All right, so this is problem 3B.6 in the Transform Phenomena book, second edition. So, yeah, it's circulating axial flow in an annulus. So basically, we're just trying to find the velocity profile in this annulus. What the rod is moving up, and this rod in the center is moving up, and this circle cylinder thing is just staying still. So this velocity. The air on this wall has velocity, and the air on this wall is just v0. Or the air on this wall is just 0. This is v0 here. So yeah, so for part A, it looks like we have to do vz over v0. So we're gonna have to do some dimensionalization, and it gives us this epsilon equals little r over r, so we're going to have to change binary conditions for that as well. And it says curvature can be neglected, so because of that we're going to use radial coordinates, or Cartesian coordinates, because it allows us to, because this is kind of like what the system is going to look like. So this is v0, and then this is just like a flat plane. There's no curve. So this is what our system looks like. This is kr, r equals kr, and this is r equals big R. So at r equals kr, v equals v0, and at r equals big R, vz equals 0, or vr equals 0, sorry. Vr at kr equals v0, and vr at big R equals 0. Because again, that annulus in the center is moving and everywhere else it's not moving. So we do the equation of continuity, which is b.4-1 for Cartesian coordinates. This is the steady state term. We're just assuming steady state, so that's 0. No x velocity and no y velocity, and then we're saying the vz velocity is the same as the r velocity. Or technically I probably should have done x, but it doesn't really matter for this assumption, like what we're trying to say here. So what we get out of this is basically dr equals 0. It says vz, but it should be r. And this helps you with the equation of motion in Cartesian, because obviously you got all these no x velocity, no y velocity, and then you have this derivative is canceled out, not particularly the vz. It's just the derivative is canceled because dvz dz equals 0. So that's why that's canceled. And then you have the pressure term that's still there because it's the air is contained in a pipe, so it's changing within the pipe. And then you have the dvz dx, which is just saying that the z velocity changes with x. So as you go this direction, the velocity is changing because the velocity here is 0 and the velocity here is v0. So yeah, so we just simplify that equation, or we just rewrite the equation basically, and we get this. And we know negative dp dz plus rho gz equals p0 minus pl over L. So you can do that. There's or it equals modified pressure. So it's, yeah, this is just the same as it's the same as modified p0 minus pl over L, because this is a derivative is the final minus the initial. So if this was positive, it would be pl minus p0, but since it's negative, it's the opposite. So yeah, now we get to this equation, and this is a separable equation because there is why is it separable? Because there's only two derivative terms, and if you move them to the opposite sides, so if this goes to this side, obviously they equal each other, but then you can separate them by setting them equal to the same constant. So set them equal to each other, and then you can separate them out and say they're equal to the same constant. Which, did I do that? I divided by u. Okay, yeah. Here I set them equal to the same constant. So I actually do use both of these equations. I just, at first I thought I wasn't going to need to use both of them, but I do. All right. So now we have to non-dimensionalize, because if you go back to the given answer, it's in this VZ over V0 form, which I did to like capital V, and it has epsilon. It's in terms of epsilon instead of R, so that's why you need to do that. So I just said big V equals VZ over V0, and that's kind of just a contrived thing that I've made up. Yeah, just to like not have to write VZ over V0. And then I solved for VZ in terms of big V and V0. So I would plug those into, I would plug big B V0 into here, and I would plug epsilon equals R over R, which that definition was given. Epsilon equals R over R, that's given. I would plug this in for R. Yeah, so we're just transforming this equation into this equation. So yeah, since the d squared is before the VZ, you don't have to square it. But for this, because the square is second, if the square is like after R, you have to square both of these. And then V0 and R squared aren't actually part of the derivative because they're fixed values, whereas big V is dependent on VZ, so it changes depending on position, and E is also, or epsilon also changes depending on position because it's little r divided by R. So obviously that's little r is changing in position. That is the position variable. So then I'm just isolating the derivative, so I can actually take the derivative or separate and integrate. And first I just do the boundary conditions. So at R equals KR, VZ equals V0. Again, that goes back to just the system. This rod is moving up at velocity V0. This R coordinate here is KR, so VZ at V0 equals KR. And then the second boundary condition I have is at R equals big R, VZ equals 0. So that's here, R equals big R, VZ equals V0, because this annulus thing is not moving. So the air at the wall is moving at the same speed of law. Both of these boundary conditions are law of the wall boundary conditions. So those two boundary conditions come from. And so you have to convert those boundary conditions to be in terms of epsilon and big V. So yeah, so basically you just plug it into the formula. So epsilon equals little r over big R. So in this case, little r equals KR. So epsilon equals KR divided by R, which equals K. And in this condition, VZ equals V0 and big V equals VZ over V0. So since VZ equals V0, big V equals V0 over V0, which equals 1. And at R equals big R, VZ equals V0, epsilon equals little r over R. And in this case, little r equals R, little r equals big R, so epsilon equals big R over R. And big V equals VR or VZ over V0. And in this case, VZ equals 0, so big V equals 0 over V0, which equals 0. Okay, so now we basically just integrate that before equation twice, or separate and integrate this twice. It's pretty simple, just separate and integrate. So yeah, you just multiply this over, and yeah, just separate and integrate. So you just integrate epsilon, you multiply epsilon and then add a C1, and then you integrate a second time. It's epsilon squared divided by 2 now. Multiply the second epsilon to C1 and add the C2. So now using the other separable equation from earlier, this one, to just solve for b, which if you look at this, it's just, it should be negative, right? No, it's positive. It should be modified PL over P0 divided by L, because dz is just the length of the pipe, the final minus the length of the pipe at the initial, and the length of the pipe at the final we're saying is L, and the length of the pipe at the initial, or the coordinate at the initial, is 0. So it's just L minus 0. So yeah, I mean, obviously look at that there. Yeah, so we insert that back up here, and that just makes it easier to solve for that. So yeah, we insert that into the above this formula here. We insert that in there for b, and that's just another parameter that we get rid of. So now we can use the boundary conditions. Usually I like to do the boundary condition that results in the velocity or whatever on this side being 0 first. So then it's easier to solve for like a boundary condition in terms of the other boundary condition. So I just plug in the conditions, isolate C2 in this case, but you can do either one in this case. It's not really easier either way. I just chose that. And then we're going to utilize the other boundary condition, plug in all the terms, and I'm going to plug in the definition from earlier, this definition, into this equation for C2. So yeah, that just kind of just makes it easier. It kind of skips a step. Yeah, so I isolate C1 terms and these pressure terms, factor out. So this is just like this pressure term times 1 minus this pressure term times k squared. So it's 1 minus k squared, and then you have this extra 1. And then this is k minus 1 times C1. So yeah, so now we divide by k minus 1 to isolate C1, and we get this, and just some simplification with algebra, and that just simplifies this term here, and you get, does that make sense? Yeah, so then I pull out this positive, goes to a negative because this is a negative here. Yeah, so then we plug in C1 into the definition from earlier, plug C1 into this definition here, and we can get C2. So yeah, C2 is this. So I'm just going to try to make it neater. So I'm going to factor out this pressure conglomerate, which I call it. And so there's the negative 1 from here, because this is a negative sign, and then we got the, does that make sense? Or wait, is it a negative sign? Does that make sense? Yeah. Okay, so yeah, this is the negative, and then there's a negative here and a negative here. So yeah, that goes to positive. And then you get the k from here as well. So that's where that k comes from. And then you have to add this again, or subtract this, because it's just the leftover term. So yeah, C2 equals that. So now we're inserting the integration constants back into, from, where is it? This equation. So we're inserting the integration constants back into that equation. So that's what we do. C1, C2, or C1, C2, insert those back into here. And it's a long equation, so I have to add some dots and do all that. So I'm going to factor out the pressure term again, just this PL minus P0 R squared 2 viscosity LV0, and we have a 1, a K, or -1, K, and a +1. So it's just going to be K, or it's going to be K epsilon, actually, just K epsilon. Oh, wait, no. I don't know. Just look at the equation, man. Okay, so yeah, epsilon squared minus, or yeah, minus epsilon K, and then the plus. Where's just the plus regular K coming from? Where's that coming from? Oh, it's right here. Okay, yeah, so that's where the regular K comes from. And then you just add all the extra terms. And yeah, I think these cancel. This looks like it cancels here, but oh, I know, because it's multiplied by epsilon, so that's why it's not canceling. Okay, so combining common denominators. So I'm just combining these two terms here because they have a common denominator, epsilon minus 1 over K minus 1. And so this is where it kind of gets interesting, and it's kind of like, wow, how are you going to get rid of all of this like crap terms? Well, since the system, look at this here, there's no airflow, there's no way for the air to get out of the annulus. So you can say that the mass flow W equals 0. So that mass flow W equals rho integral Vz over dA. That's just like a definition that you should know. I could probably derive that, but nah, I'm just not that guy for you. So yeah, we use this definition with 0, and because there's multiple terms in this equation, we can separate. So like we can integrate this term and we can integrate this term separately. We can move one term to the other side, and then we could divide this because it's not part of the integral. So it allows us to isolate that term and solve for it in terms of epsilon. So that's why we're doing this whole mass flow thing. So you can just get rid of this annoying term that just doesn't like jive with everything else. So actually finding dA, dA is just the differential area that's perpendicular to the flow direction. So in this case, the flow direction is, why am I doing it like that? Why does it look like that? Does that make sense? I think it makes sense. Flow direction. Yeah, okay, that makes sense. So flow direction is either up or down. Okay. Yeah, so differential area is this area, which is perpendicular to the flow direction. So you got the delta R, which is this smaller part, and then L, which is kind of just an L prime, which is kind of just an arbitrary variable. Which it's going to be divided out anyway, so it doesn't really matter because the equation equals 0, so we can just divide out whatever we want, really, as long as it's not like a variable like epsilon or R that's going to be part of the actual integration. So we're writing out the integration, and again, looking at this is in terms of the big V and the epsilon, so we need to change it. So yeah, here I'm just dividing out unwanted terms, and I'm dividing by R because it's convenient. You'll see later with our equation. It makes it, you don't have to divide out R, but if you do, you have to do less simplifying later, so that's why it's done. So yeah, we don't have an expression for Vz, but we have Vz over V0 equals big V, and again, that's because that's what it gave us for the answer that it wanted. Since big V is in terms of R, we have to use epsilon. Again, that's because the problem answer was in terms of epsilon, so that's why we're using epsilon. if epsilon ranges from little r to big R, or if epsilon equals little r over r, then epsilon ranges from r over r, which is the larger value 1 to kr over r, or k, which is the smaller value, and that's the inner annulus radial value. And this also means that d epsilon equals dr over r. And that's, again, because epsilon equals little r over r. So you could just say add the d's here. I don't know why. That's just how it works, Brody. Yeah, because epsilon equals r over r, little r over r. Thus, the equation transforms to the following. Big V equals d epsilon. So since d epsilon equals dr over r, we have the dr over r. That was the simplification earlier. That just made it easier. Dr over r. So yeah, it just makes it easier. And V0. I think that's actually, there's Vz equals big B, big V0, but then you just there should be a V0 here, but you just divide it out because it's equal to 0, and V0 is not, it's a fixed value. It doesn't have epsilon in it, so you can just divide it out. So technically there's supposed to be a V0 here, but just divide it out and it's fine. So now we're inserting our expression that we solved for earlier for the big V. Obviously this is pretty self-explanatory. Just copy paste what we got earlier. And because there are two terms in integration, one with the pressure conglomerate and one without, we can integrate these separately, move this one over to this side of the equation, and this is going to be outside of let me just show you. So we have these two separate integrals. We move this one over to the other side, and then we take this out of the integral because there's no epsilon, these are all fixed values, so we could just take it out of the integral. And then we could divide this while leaving this here. So divide this to the other side while leaving this here. So then we can solve for this. We have these two integrals on top of each other. So that's kind of cool. And then we just do the integration, which is kind of annoying to look at and just do because it takes a long time. Yeah, we solve for this, just do the integration. It's a pain in the butt. Yeah, we're taking a common denominator of 6, so and that's because it makes it so all of these are whole numbers in the numerator and the denominator. So dividing by 6, so you multiply all these top things, or you multiply all these numbers by 6. So this would be 2, 3, or 2, -3k, -3, 3k, whatever. So that just goes in here, and you divide by 6, and yeah, it just makes things easier. So yeah, this is you can simplify this algebra, and this algebra here actually too. Yeah, so this equals that, and that lets you just separate those terms into this, and this equals negative this. So, and this equals that. So that's just factoring stuff. Sorry. Oh, never mind. I just do k, but I just do, what do I do here? Oh yeah, so 1 minus k, this cancels with that, so that's where that term goes. Yeah. Okay, so now we bring the 6 up to here, and we get 3 times k minus 1 over, or we just get 3, and then we can cancel this with this, and we get squared in the bottom. So then we get this nice expression that we can insert back into big V again, and we get this. Woo. Yeah, so now big V is in terms of epsilon only. So yeah, so basically, I think I fudged up something with I think I was supposed to solve this thing in terms of 1 minus k and not k minus 1, because if you look at here, they use 1 minus k and I use k minus 1, so probably just distribute a negative sign somewhere, but I did Google Doc. All right, found the proof. So this is the given formula. Yeah, just look at that, and then this is from here. This is this formula. If you look at thing, it matches, and then going to my formula, the other formulas are kind of just trying to do simplification, but it didn't work out. Simplification was incorrect. So this is the correct formula here, and then this is the derived formula here, which is this. You just check that if you want, but it's the same formula. So then I did different epsilon values from 0.5 to 1, since I set k equal to 0.5. The least or the lowest epsilon value has to be 0.5, because epsilon equals little r over r, and since kr is the smallest r value, kr divided by r equals k, and our k equals 0.5. So the lowest epsilon is 0.5 in this arbitrarily set k value of 0.5. So I did epsilon from 0.5 all the way down to 1, which would be where epsilon equals r divided by r, and that equals 1, obviously. So plugging in all of these different values, we see that the absolute difference between these two equations at all these values is pretty much 0. So we can safely say that this equation is the same as this equation here. So, and I did the same with part B, actually. So I guess if you don't like that I didn't simplify it more in depth to be the exact form, and rather just did a proof, I would say probably click off, because yeah, I just couldn't be bothered to do the complete simplification. Yeah, I tried, actually. I think I had to do the 1 minus k instead of k minus 1 from the start, because the form was just so different. It was just really annoying to do. Okay, so now we're in the part B. Part B is it's just not doing an assumption with the no curvature. So we're saying that there is curvature, and the system actually does look like this. So we're going to have to use the cylindrical coordinates, because it's a cylinder, obviously. It's not a sphere. So yeah, cylindrical coordinates. So yeah, these B.4-2, these are cylindrical coordinate. This is the equation of continuity for B.4-2. D rho dt, that's again the steady state term. We're assuming steady state. No radial velocity and no v theta velocity. So we get d dz rho vz equals 0. And from that we could say dvz dz equals 0. And that just helps us with that equation of motion. And we're using B.6-6 because this is the this is the VZ equation of motion, and if you look at the given answer, it's in VZ coordinates, or the velocity is a VZ velocity. It's VZ over V0, so that's how you know you're trying to get VZ. So yeah, I just wrote out the whole equation. Again, dvz dt, that's steady state. VR is canceled because there's no radial velocity. V theta is canceled because there's no radial velocity. And then dvz dz is canceled because of the equation of continuity. So yeah, if you're wondering why you have to do the equation of continuity, it's just because of it lets you make this assumption. Your teacher might not or your teacher might not require you to use it, but that's where it comes from. That's why you have to. That's why you have to, in quotation marks, use it. So we got dvz dr, and then that's the radial velocity, or the vz due to the radial direction, and obviously the walls are extending in a radial direction, so that's why that's a thing. And then dp dz, that's like the height. That's, yeah, it's still there. And then the vz v theta, I think this is actually an assumption that was made in the problem, because normally you wouldn't be able to just cancel this assumption out or cancel this out, but I think in the problem it states that you can't do that, or that the velocities should only be due to the radial coordinates. Let's see. Shields, rings. No, it doesn't say that specifically, but yeah, obviously to just get the correct answer, you have to. Well, oh yeah, it's a symmetrical system, so that's why, because it's symmetrical. There's no difference from here to here, so theta, this direction around, it's not going to make a change. So I guess that's why you can get rid of that term there. System symmetrical. I mean, yeah, that's the skin is pretty bad, but yeah. So so you write out our simplified terms. We have this pressure again. That's going to be condensed there, and then yeah, because this is negative, it's P0 minus PL when it's negative over L, because again, the length, total length, L minus 0 equals L. And then you get this. Yeah, this is a plus here. Sorry, this scan is terrible. Probably should have redone it, but sorry. Yeah, I'm not going to do it. So yeah, here I'm just isolating the derivative, so I can separate and integrate. Isolate derivative, and then we're integrating. So we have the r, multiply this by r, or this by r. No, wait, does that make sense? Or yeah, it's r, so it's already multiplied by r because the r is from here. Yeah, okay. So yeah, so you just do the integration. It's r squared over 2 now, plus c1. Isolate the derivative again. Isolating from here to here. Divide out the r, and that's why this is regular r and not r squared anymore. And then derive again. It's r squared over 4, and then ln r, because 1 over r, or integral of 1 over r is ln r. So now we got to modify the equation to fit the capital V. Well, actually, yeah. So yeah, you can modify it. In the part A, I modified it at like this stage, but you can modify it after you do the integration as well. That's an option. So yeah, I just equals VZ, so I set VZ equal to big V over V0 and R equal to RE, because these are the equations. Big V equals that, big V is that. And I just inserted these definitions in for little r and VZ. So then we get, yeah, this is VZ, little r. And then I divide by V0 just because I just wanted to isolate the V, because the big V, because that's the form it comes in the given equation. All right, so boundary conditions, same boundary conditions as before. And we're just plugging it in here. Yeah, it's the same boundary conditions as before. Isolate C2 with the first boundary condition, or with the boundary condition, with the second boundary condition, because this one is 0, so you can set it to 0. You can set one side to 0 and it makes it isolating easier. Solve for C2 in this case is easier because there's this L and R in the C1, so solving for C2. And then you use the other boundary condition while plugging in this definition for C2 into the equation. And we have C1 only, so then you solve for C1. That's what I'm doing there. There's a little identity there to help you out. Let's see. So yeah, I eventually solve for C1 in like a somewhat decent looking form. And then we plug C1 back into the equation from earlier. Where is it? This equation. Plug C1 back into this equation to solve for C2. Then we get C2. And then again, factoring out this pressure conglomerate thing just to make it look better. And so when you integrate it, it makes it easier later with the mass flow equals 0 thing. Yeah, so simplifying, doing all that. Yeah. So yeah, again, the mass flow thing, mass flow equals 0 because it's a closed system. So differential area of this is the area perpendicular, differential area perpendicular to the flow direction. So the flow direction is it's going up, or it's going up and down technically because it's like reciprocal. So yeah, the thickness of this is delta R. The length of this is 2 pi R, 2 pi regular R, because that's the circumference of a circle. And the length of the outer is 2 pi, in parentheses, R plus delta R, because this radius here is R plus delta R on the outside. The outside radius is R plus delta R. So to find differential area, it's basically you're subtracting the circles. So this R plus delta R circle is like, think about it, it's like this whole circle here, and then the inner circle is like this circle here. So you subtract them basically, and this inner center part doesn't matter, even though it's taking a chunk out of the circle, because you're integrating with limits. So like this limit is KR, so it's fine. So dA equals pi, it equals this, and then you just expand this out and cancel terms. That's r squared, and then you cancel this delta r squared, because think of delta r as like an infinitely small quantity. So if you square the infinitely small quantity, it's going to be like infinitely small. So even on the scale of delta r, it's like infinitely small. So you can cancel that out. So then dA is just 2 pi r delta r, or 2 pi r. Yeah, delta r, this delta r and this is the same thing. So yeah. So we're going to need dA in terms of epsilon, and remember r equals big R epsilon. So and dr equals big R d epsilon. Just the d's are like, you just add the d's in, I guess. I don't know. It should make sense, sure. Thus dA equals this, and then yeah, 2 pi r squared epsilon d epsilon. And again, the only thing that really matters is this epsilon here. You could just, you'll see later, I just divide the 2 pi r squared out because it equals 0, because the one side equals 0, so you could just divide it out. And again, you have to change VZ for V for big V, but it doesn't really matter because you're going to divide the V0 out because the one side equals 0, so you could just divide it out. But you wouldn't be able to divide this epsilon out because it's part of the integral, so you can't divide the epsilon out. And you can't divide the big V out because it has epsilon in it, and you got to integrate. So yeah, all these 1, 2, 3, 4 are constant values, so that's why you can't divide them out. But the big V and the epsilon you cannot divide out. So yeah, you just have this left. So then we insert the expression that we solved for earlier for big V with this pressure conglomerate term that we want to get rid of. Our objective with this whole process is to get rid of this pressure conglomerate thing. So yeah, we separate the integrals. So this was one term and this was one term, but you can separate it into two separate integrals because they're just added together. So yeah, then we take this pressure conglomerate out of the integral because it has no epsilon terms in it, and it's just being multiplied to this whole thing, so we can take it out of the integral. Here, I multiply epsilon times, I put this epsilon into the parenthesis here, so just skipping a step kind of. Yeah, subtracting because it's going to the side of 0. And then we divide by this integral, and we get this. So just integrating out here. Yeah, I just did Wolfram alpha, I guess, for this. Or did I? Yeah, I think I did. Yeah, basically this is just a bunch of simplification. That's just really annoying to do. Yeah, I mean, you can look at that. It's pretty self-explanatory with the little note things that I did. Multiply numerator divided by -4 to make it look cleaner. Yeah, that's just because the highest dividing thing here is 4, and it's a common denominator with all this, or least common, most common denominator, whatever, something like that. Elementary school stuff. Yeah. So I distributed that. I distributed lnk to. I multiplied lnk up to the numerator. I don't know. I did something with this. Basically, it's just look at that in depth and you'll be able to figure it out. So then, yeah, the pressure term equals this. And then I get this crap ton equation. And yeah, again, I just didn't really feel like simplifying it because in real life, obviously, you're not going to have the equation. You're just going to like be testing it against whatever. I'm just making excuses because I'm lazy. But I did prove it that it's right. For part B, yeah, again, so this is the given equation. It's a really long thing, but it does match. Sorry, it's so long. And then we got our derived equation, which is equally as long, pretty much. Let's go back to here. Control minus, gonna do that. Like, get that out of the way, maybe. Okay, that's the whole thing. So yeah, derived, it's just this whole equation, just converted into Excel format. So yeah, absolute difference. This is again just absolute value, this minus that. Same deal with earlier with the K values and the epsilon values. Oh yeah, by the way, this is just a um, arbitrary amount of values that I'm using. It's not really like the 0.05 interval. It's not like a specific thing. It's just what I did. So yeah, you see the absolute differences are like e to the negative 16 different. So that's close enough. Yeah. So I don't feel like simplifying it. So yeah. If there's any questions, feel free to comment down below. If there's any problems that you want solved in the future from this book, or like mostly from the like chapter 1 through like from the first 3 chapters of each section, that's mostly my expertise or whatever. But I can do other problems too. I've done some other problems for other classes. So if you have any questions about this problem or um, things that you should think I should be doing better for this channel, feel free to suggest that as well. All right, signing off. Bye bye.